So good evening everyone and welcome to the 7th session for the course Measure and Integration. Today I will be mainly discussing about the differentiation and fundamental theorem of calculus that you have learned in analysis in the setup of Lebesgue integration, and instead of differentiability we'll have a differentiable almost everywhere. Okay, so let's start with the classical second fundamental theorem. Okay, so this is the theorem that if you have a Riemann integrable function, okay, if you have a Riemann integrable function, so f is, so this small f is basically a derivative of this capital F. Okay, so f prime is f, then what you have is that integral of this f prime, okay, on some interval a b will be equal to the difference of the end value. Okay, so this is what you know from your last courses on analysis. And then our goal would be, so instead of this condition that f is Riemann integrable, we'll try to assume that f is Lebesgue integrable, and instead of this that it is derivative of a function, we'll have a function which is derivative almost everywhere. So these are not equal, but instead of this condition we'll have almost everywhere. Okay, so there will exist a function f such that this thing happen. Okay, so then we'll try to see what else can be said. Okay, so coming to the example of Cantor function. Okay, so this Cantor function I think you have seen in the earlier session. So this Cantor function f is a monotone continuous function. Okay, and at 0 it takes the value 0, and at 1 it takes the value 1. Okay, so it's basically an increasing function which is continuous. And if you remember the definition, it was constant on the complement of the Cantor set, right? So if this is 0 1, so at first step this was the interval which we removed, right? So this is 1 by 3, 2 by 3, and on this interval this was constant, and then this sort of construction again at different level we'll have. So this was the sequence. So ultimately the Cantor function was constant on the complement of the Cantor set, right? And if you know that the Cantor set, so 0 1 is Cantor set union its complement. So this Cantor set, it is of measure 0, right? So Lebesgue measure of this set is 0. So we don't care about this set, and we know that f is constant, okay, on Cantor on the complement. Okay, so on each of the part it will take the value, it will take different value, but on each of the thing, okay, so it is constant. So on the complement of the Cantor set it is differentiable almost everywhere, and in fact the derivative will be 0 just because it's constant there. Okay, so this is what it says. So we know that this Cantor function is almost everywhere differentiable with the derivative 0 almost everywhere. Okay, so now if we try to calculate this integral, since this function f prime is 0 almost everywhere, the integral is 0, right? So this integral is 0, but if you take the difference of this end values, you are getting 1. So it clearly says that if I remove from this statement, if instead of this Riemann integrable, if I put Lebesgue integrable, okay, and over here if I write all which is derivative of a function f on AB, instead of this I write on AB almost everywhere, then clearly this is not true, right? So this is becoming false. Okay, so that's why in this session we'll see that for what function this will be true. Okay, so it's clear that for in this setup it is not true, so we'll put some restriction on the function f so that we get this type of result if possible. Okay, okay. Okay, so let us first see this fundamental theorem of calculus for monotonic increasing function. Okay, so let's say that you have a function f which is monotonically increasing and which is, okay, so this is the monotone function which is increasing. Then you have that f is differentiable almost everywhere, okay, and the derivative f prime is measurable, and this integral will not be equal to the difference, but it will be less than or equal to this difference. Okay, so over here we are just using this monotonically increasing function, then this implies that it is differentiable, and in fact the derivative is integrable, and this integral of this derivative is less than equal to the difference of the function at the endpoints. Okay. So you can clearly see our Cantor function, what the example what I gave, so that is monotonically increasing function, okay, and it's in fact differentiable almost everywhere, okay, and this was coming to be 0 and this was coming to be 1 in that case. So this Cantor function shows that this inequality can never be equality, it cannot be possible, okay. So at most what we can say for such function is that the integration of the derivative will be less than equal to the difference of the function at the endpoints, okay. Okay, and for the proof, I mean to prove this theorem, okay, you need some Vitali covering thing, okay. So what is that Vitali cover? So if you have a collection of intervals, okay, suppose you have a collection of intervals which cover some set E, okay, so E is given to you and a cover is given to you of that set, then this cover is said to be Vitali covering of E if for any epsilon, okay, whatever epsilon you choose, you can find a, and for any x in the set E, you can find the interval, okay, which will contain that point, and that length of that interval will be less than epsilon, okay. So it's like, I mean, you choose any point, you give me any epsilon, I will say that okay, there exists one interval I. So suppose this I, this is some collection I alpha, where alpha belong to some set lambda, okay. So this is the index set. Then if you give me any x in x, or sorry, in E, which is covered by this collection, and if you give me any epsilon greater than 0, then I'll have some I alpha naught in this collection. So I alpha naught belonging to this I, such that x belong to I alpha and the measure or length, okay, of I alpha will be less than epsilon, okay. So I mean every point is contained in very infinitely small interval, that's all it says. So cover will be said Vitali cover or Vitali covering of that set if for any point we can find an interval in that collection which is of infinitely small length, okay. So whatever small whatever length you give, I can find some interval I such that x is in that interval, okay. So that's all about this definition of Vitali covering. So this is called Vitali covering lemma. What it says, that suppose you have a Vitali covering of E, okay, then for any epsilon there will exist, so this n, obviously this n will be depending on epsilon, so for any epsilon there will exist a finite collection of intervals of which is coming from that Vitali cover I, such that the outer measure of this E minus union this thing is less than epsilon. So it's like, I mean any finite interval you choose, I mean for given epsilon you will get a collection of intervals of, I mean finite many intervals which is carrying the whole measure, okay, because if you see on the complement, its complement can be made very small, okay. So all the measure of the set E is, most of the measure is being carried by this set, okay. So it's a finite set, but still the measure of this is quite large, I mean very close to the measure of E, outer measure of E. See, E is not given to be measurable, so we can only talk about the outer measure, okay. So that's all it says, that if you have a Vitali cover, then for any epsilon you can find a finite collection of intervals from that cover such that the outer measure of its complement, union of that complement, will be very small, okay. So for this n will depend on this epsilon, okay. So that's all about this Vitali covering lemma. So these tools are basically used to prove this theorem, okay. Okay, so now let's go to the function of bounded variations, okay. So what is that? So suppose you have a function f, okay, and consider the partition of the interval AB, okay. So this is Suppose this is your A, this is your B, then you have a partition, let's say x0, x1, x2, like this, and this will be some xn. Okay, so this is the partition of this interval AB. You define this quantity which is t of corresponding to this partition P and for the function f. Okay, so this is a function which is always greater than equal to 0. Okay, so what this function does, so suppose you had this, now suppose your function is maybe given by something like this. Suppose this is your function, then what it says, that what this calculate, so you have this partition, maybe I can put it here. So you have this partition, and now corresponding to this, so suppose this is xn minus 1, so this is the value at xn, and this is the value at xn minus 1. So consider this difference. Okay, so mod of that difference, consider this x1, this x0, and this difference. Okay, x2, x1, and then this difference. So what you do, so each difference you add up. Okay, so this is what you are doing. So you are considering how the functions is varying over the interval AB. So for given a partition P, so this is the summation of all these differences. This is called T, this function is called T of corresponding to this partition P and F, T of PF. Okay, so now so this is a quantity. Now we'll define what is total variation of F. Okay, now if we take supremum over all such partitions, then that quantity is called total variation of the function F. So how the function is varying in the domain AB. Okay, so this is called total variation of F over the interval AB, and this is how it is defined. Okay, okay, now the function F is called bounded variation. Okay, it is called to be of bounded variation if this quantity is finite. So if the variation of the function f is finite, we say that the function is of bounded variation. Okay, I hope this is clear. This is just a definition. Now let's see some example of bounded variation function. So suppose you have any Lipschitz function you take. Okay, so that Lipschitz function is of bounded variation. How can you see that? So suppose f is Lipschitz. Okay, what does this mean? This means that there exists some L greater than equal to 0 such that mod of fx minus fy is less than equal to L mod x minus y. So this is what it means when we say that a function f is Lipschitz. Okay, and then what you have to prove? You have to prove that if you take any difference, okay, it will be finite if you take supremum. So consider you have this f. Now let xi, I equal to 1 to n, be any partition. Okay, so you choose any partition of this AB. Then what you have to, first let us see what this TPF will be. Okay, so then T, so let's say this P is called the partition. So TPF, if you go to find, what will be that? It will be I equal to 1 to n mod of fxi minus fx I minus 1, right? Now you know the function is Lipschitz, so you can use that, and then you will get L summation I equal to 1 to n mod of xi minus xi minus 1, right? This is what you get. Now now what you have to prove? So okay, so this is there. Now each of this difference, okay, now if you want, you can consider this partition. So this partition is something like xi less than xi plus 1. Okay, so it's sort of increasing. So if you have this AB, so this is your x0. Okay, so I should have mentioned it here, but I am writing it here. So this is x0, x1, x2. So it is increasing. If you increase the index of x size, the value is also increasing. Okay, and then it will finally reach xn. So this modulus will now become, the modulus we can remove that. Okay, so if you want, you can remove this modulus just because that is positive quantity. So you can, this is what you get. Now if you sum it up, what you will get is, so there will be cancellation at each state. So it's like x1 minus x0 plus x2 minus x1 plus like this. So ultimately you will, at last you will get xn minus 1. Now this x1 will cancel with this one, this x2 will cancel with this one, so it will be some telescopic sum sort of thing, and you will get x at n minus x at 0, and this is nothing but x of n is b and this is a, so this is L of b minus a, and this is finite. Okay, so any Lipschitz function is a bounded variation. I mean, is this calculation clear to you?
So, the partition, whenever we have the partition of AB, it is always of the increasing form.
No, I mean, the partition what we take is of this sort. So x0 less than x1, x1 less than x2, x2 less than x3, like that. Right?
Yes, sir. Sir, that means if we don't, मतलब कि हम इसको decreasing form में नहीं लिख सकते.
No, it's just a partition. If you want, so when we consider this thing, we consider in this fashion, that's all. So it basically says, I mean, how to say, if you're writing some partitions, so suppose this is AB, okay, now it's not like increasing. So suppose you are partitioning this thing, so this, suppose this is the partition, right? Now you are just naming it, giving it name. So naming it is like you're assigning x0, x1, x2, like this. You are just giving name and nothing else. I mean, it's not like increasing in the sense of index, that's all I said. So it's just like you're giving some name, that's it.
Okay, sir.
Yeah, so I mean, instead of this, if you want, let's say you have just 3 points, okay, suppose this is the only part, so you can say this is my x, this is y, or m n o, like this. So this is, there is nothing like increasing in this way. But here what you will do, fn minus fm. This is the definition what you use, that the higher index, I mean, which is the larger one, and then minus this one when you consider this sum. That's why you take, I mean, and it's just a standard way of doing so, nothing special about that. Okay, so this was all about that. Any Lipschitz function you take, that is of bounded variation. In a similar way, since you take any C1 function, now C1 function means the derivative is continuous. Now the moment you say the derivative is continuous and this interval is compact, so it is bounded. So it basically means f is differentiable and f prime is bounded. Okay, so this will imply that f is Lipschitz. Okay, and hence f is Lipschitz, and hence f is of bounded variation. Okay. In a similarly, you can show that this monotone function, if you take, that is of bounded variation. Okay, and for showing that, the only change will be this one, that instead of this mod you will get this thing. Okay, and again you will have cancellation, so what you get is fb minus f of a. Okay, so this is also a bounded variation, monotone functions. Okay, so far what you have seen, that this Lipschitz continuous, I mean, are of bounded variation, but in general any continuous function need not be of bounded variation, and this is the example. So if you see this function fx, this is continuous, so this is a continuous function but not of bounded variation. Okay, and how can you show that? So consider this partition, this p, you can consider it as, so let's say you include this 0 1, okay, and then you take inverse of odd multiples of pi by 2. Okay, so it's like pi upon 2, just a second, no 2, and then here it should be pi and then 2k plus 1. So 2k plus 1. Yeah, you just, so, and then since this is square, just take square root and then take k equal to 1 to n. You can clearly check that this quantity will be always less than 1. So this forms a partition. And now if you try to evaluate this t of pf, okay, so this is nothing but modulus of, so okay, in summation, so let's say this is my, if you want to name this, let's say this is my xk, okay, so this is xk, okay, so if you want you can like I equal to 1 to a mod of f of xi minus f of xi minus 1, okay. If you calculate this, ultimately what you will get, so let's see what you get here. So it will be summation I equal to 1 to k. If you put xi in this function, so you'll get xi square and sine of 1 by xi square minus xi minus 1 square sine of 1 by xi minus 1 square, okay. And then, so see, sine of 1 by xi minus a square is nothing but sine of, you do the square of this, so it will be 2i plus 1 k by 2, right? Now it is odd multiple of pi by 2, sorry, it's pi, so it's odd multiple of pi by 2, so sine function will take the value either plus 1 or minus 1. So if it's plus 1 here, then it will be minus 1 here, right? So ultimately this will be sum, okay, so it will be xi square plus xi minus 1 square, okay, just because if we are taking modulus of that. And now if you put it, the value of xi is here, so this is summation, okay. Now if you substitute that value, what you get is, so you can take pi by 2 common, so let's take pi by 2, I equal to 1 to 2, okay, this will be 2k plus 1, it will be, sorry, 1 by 2, so it will be 2 by pi, and then 1 by 2k plus 1 minus 1 by 2 of, sorry, it's not k, it's I, so 2i plus 1, and then you'll have 2i minus 1, okay, and then you have this plus sign, okay. So now if you calculate this, get 2 by pi, then you can take this, if you try to solve, this is 4i square minus 1, and then 2i plus 2i will be 4i, okay, and then you can clearly dominate this by 2 by pi summation, this will be 4i upon 4i square, right, because 4i square minus 1 less than 4i square, okay. So this will be 2 by pi summation 1 by I, okay, and this summation is from I equal to 1 to n. Now as you increase the value of n, this summation is unbounded, right? So you know that summation 1 by n is divergent series, so that's why this, where this is, so this quantity is unbounded, okay, so that this function is not a bounded variation, okay. Okay, so this was all about this function. Okay, now I'll just state the few properties of this bounded variation function. So if you have a bounded variation function, that would imply that the function is bounded, okay, but the converse need not be true. If you have a bounded function, that may not imply that it is of bounded variation, okay. So as of now you can see that a bounded variation function is bounded and if you have f is of bounded variation, then the modulus of f is also of bounded variation, okay. Okay, and then you have, if f and g are two functions, okay, which is of bounded variation, and if you choose alpha beta real constant, then the linear combination of f and g, okay, that is alpha f plus beta g, is also of bounded variation. In fact, the product of two bounded variation function is also a bounded variation, okay. Okay, so this is quite interesting characterization, that suppose if you have been given a bounded variation function, then you can you can write any bounded variation function as a difference of two monotonic functions. Okay, so one way is obvious, that if you say f is equal to, let's say, sum f1 minus f2, where f1 and f2 are monotonic, then you already know that monotonic function, I mentioned it here, that all monotonic functions are a bounded variation. So this f1 is a bounded variation, f2 is a bounded variation, and by using this proposition I can say f1 minus f2 is a bounded variation. So if f is difference of two bounded variation function, two monotonic functions, then the function f is of bounded variation. In fact, the converse is also true, and I'll solve a problem related to this where that solution itself is a proof. Okay, so you can write this function f as f, so you can write this as t of ax f, okay, minus f plus f, plus f minus f, minus t of ax f. So this is an increasing function and this will also be an increasing function. So I'll prove it later on that how these are increasing function and all this thing. Okay, so any function can be written in this form where this and this both are monotone function. Okay, and then a corollary of this is that if a function is of bounded variation, okay, then it is differentiable almost everywhere. How? So suppose this f is of bounded variation, right? Then by this theorem, okay, by the theorem, you know that f is f1 minus f2, where f1 comma f2 are monotone function, right, by above theorem. And if you recall this fundamental theorem of calculus type for monotone functions, this one, then see, if a function f is monotonically increasing, okay, then you had that f is differentiable almost everywhere, right? So using that, you can say that this f1 f2 are differentiable almost everywhere, and hence this function f is differentiable almost everywhere. Okay, so this is immediate from this theorem and using that theorem above. Okay, so now we'll have a same fundamental theorem of calculus type of result for bounded variation function. Okay, so if you can prove this theorem, that would imply the earlier one, because so earlier one dealt with f monotone. Now suppose you are able to prove that for any bounded variation function, this okay, so let me first state what the result is. So suppose you have a bounded variation function, okay, then this f prime, then obviously f is differentiable almost everywhere by this result. Any bounded variation function is differentiable almost everywhere, and this derivative is integrable, and this integration of this mod of f prime, okay, is less than equal to the total variation of f. Okay, so this is what it says. So if you compare with this monotone one, you had this f prime less than equal to fb minus f of a. You can check that from here you can conclude this one, because any monotone function is of bounded variation, so this is true. Okay, and the moment you say that f is monotone, okay, that means either it is increasing or it is decreasing. In that case, this mod will be removed, right? So if f is increasing, then f prime is greater than 0. If f is decreasing, then f prime is less than 0. So there will be no role of this mod. Okay, so either it will be plus or minus. So either it will be plus minus, right? So this will be there, and if you calculate this total variation, you will get this fb minus fa or fa minus fb, depending on, I mean, whether the function is increasing or decreasing. So you will have, this will be also plus minus. Okay, and this will prove the result what I stated earlier for monotone functions. Okay, so So this proposition implies FCT type result for monotone function. Okay, so this is generalization of that above theorem. Okay, so this result is generalization of that one. Okay, and if you have this f is C1, okay, that f is continuously differentiable, then this inequality is actually an equality. Okay, so it's more close to the classical fundamental theorem of calculus, that if you have the derivative and the derivative is continuous, then that would imply f prime is Riemann integrable. Okay, and hence it is Lebesgue integrable. So this f prime will make sense, mod f prime, and you can prove that this will be equal to the total variation of f. Okay, I hope these things are clear to you. So if you have any doubt, you can stop me then and there. Okay, so is everything clear so far?
Yes, sir.
Okay, now next you can actually prove that this result of C1 function is in fact true for in any dimension. So far we were talking about real valued function, but here we are talking about vector valued function. So these are vector valued function. Okay, and you can prove that this fundamental theorem of calculus is true for any C1 vector valued function. Okay, okay, yeah. Okay, so this was all about this bounded variation function. Now this is just an application of this theorem, this one. Okay, so what it says, so suppose you have a curve. Now curve is basically a function from a bounded interval. Okay, so this curve is just a function from AB to R2. So it's something, so this is a curve, for example, like this. Then for you can define, so suppose this is A and this is B. Okay, so if you, so this function, this is gamma of x or gamma of t if you want. So suppose this, if you partition this interval AB, so suppose this is your x0, this is x1, this is x2, and so on, you have this is xn. Okay, so suppose this is the partition you have. Now if you try to calculate this gamma xi minus gamma xi minus 1, so you will have this type of summation is there. So this is called the approximation. So arc length is nothing but, I mean in general, I mean English language, what do you mean by arc length? So basically the length of this curve, right? So this is my arc length. Okay, now the question is when you can calculate this or when you cannot. Okay, so suppose you try to evaluate this difference, gamma of xi minus gamma of xi minus 1. Okay, so it's like, so this is there, so what it is, so you let me show you properly. So suppose this is my x0 and this is corresponding to x1. Okay, now this is the difference, gamma of x1 minus gamma of x2. Right? This is the difference. So let me use some other color. So this is the difference, right? This gamma of x1 minus gamma of x0, and this is your x1 minus x0. Okay, and this, consider this triangle. Okay, so if you try to bring these points very close, so this curve, okay, will converge to this curved region, right? Yeah, so for if you want, you can consider, so suppose instead of this curve you had this line, straight line, then obviously this is your gamma of xi minus gamma of x0, and this is your x1 minus x0. I am saying when you come close to this one, these two value will be the same. Okay, so we are approximating this length, the length of this curve, okay, the length of this green curve by this perpendicular distance. Okay, this difference of gamma x1 minus gamma x0, and this is in fact, I mean, these two things, if this difference, if this line is very small, then these two are, I mean, if you take projection of this line, this is this basically this one. So if you make these the base very small, then these two are basically coming to be the same. I mean, they are the approximation of this, sorry, this green line, this green curve. Okay, so that's why I have this is called approximate length, that you are considering the difference of this sort, that gamma xi minus gamma xi minus 1, and then you are adding this. So this is not the exact length of this curve, but this is an approximation of this length. Okay, so suppose you have this approximation. Now this curve will be called rectifiable curve if this length is well defined. That means you have some value for this green curve, I mean. Okay, now suppose you take supremum of this one over all partition. Now you make the partition more finer and finer and finer, then this will converge to the length of this function. So that's why if you take supremum of this quantity, you will get length of the curve gamma. Okay, now when this supremum exists, this supremum will exist if gamma is of bounded variation. Okay, so this is how this bounded variation function is related to curve. So the curve gamma is said to be rectifiable, that means its length is finite and it can be calculated if gamma is of bounded variation. Okay, so now assume that this gamma is of bounded variation, then this gamma has some length. Now using this theorem, when you say that f is of bounded variation, okay, so in this particular case assume that this gamma is c1. Okay, this curve what you are giving, this gamma of x, let's say you have this c1 or not this one, then you can, and also assume, so okay, so this c1, what does it mean? That if you take some parameterization, so suppose this x, so if you write this map, what is gamma of t? So this is nothing but it is a coordinate in this R2 plane. So suppose this xt comma yt is parameterization of this curve gamma t. Okay, then c1 basically means that this xt and yt both are a c1 function. Okay, so suppose this parameterization is c1, then from this result, if it is c1, then obviously this is of bounded variation, and this integral will be called the total variation of this function. Okay, so this length of gamma, which is equal to the total variation, I mean from here what I said just now, that the length of gamma is nothing but supremum of this thing. Okay, so this length of gamma is equal to the total variation, and from this theorem you know that the total variation of function is nothing but the integral of mod f prime, so which is equal to integral of f prime. And what is f prime here? So f prime basically means, okay, I think, let me correct this, so this is gamma and this is also gamma. Okay, so length of gamma basically means total variation of gamma, which is equal to the integral by above theorem. So this is by last theorem. Okay, and this gamma prime is nothing but, then this is not usual mod, but this is mod in R2, which is norm in R2, which is the Euclidean norm, and this is this one, root under of x prime t square plus y prime t square. Okay, again here is, just a second, so here this is missing, yeah. So this is equal to, so the length of gamma is calculated by this quantity. Okay, and this I think you must have seen in some curves and surfaces course, that this is gamma prime. Okay, I mean the length of gamma. Okay, so this was all about this bounded variation function. Now let's go to the first fundamental theorem of calculus. Okay, so if you recall that, it basically says that if you have a Riemann integrable function f, and if you define fx in this form, okay, and then f will be differentiable and f prime of x will be fx. Okay, so that's all you have seen in your analysis course. Now here what we are doing the same thing. So here we assume that let f be an integrable function. Okay, so our goal would be to give some analog of this theorem in the setup when the function is Lebesgue integrable, and instead of differentiability we'll talk about almost everywhere differentiability. Okay, again the same thing. Okay, so let's start this with this proposition. So it says that suppose you have a function f which is Lebesgue integrable. Okay, and then this, if you define this integration, I mean f of x as indefinite integral of this f, okay, then this function fx is uniformly continuous and of bounded variation. Okay, so what does this imply? That you cannot write, so suppose you're writing, so suppose f is given to you, then the question is, can you write f of x as this one? So suppose f is a given function such that f of prime is integrable. Okay, then can you write in this fashion? Is this true? Right, that is the question, that will this be true? Okay, then the answer is no, because of this theorem. This says that the moment you write this as an integral, okay, so this integral function, this indefinite integral, okay, this is uniformly continuous and of bounded variation. Okay, now when you write this fx is given to you a priori. Okay, now this, suppose you take f to be which is not uniformly continuous, let's say, then you cannot write it in this fashion, because this theorem tells you that this quantity is uniformly continuous and bounded variation. So if f is this capital F is not so, then this equality cannot hold, right? Okay, so you, from here what you can conclude, that this, so if suppose this, if you go to the analysis setup, when this f prime is Riemann integrable, and suppose f of a is 0, then you know that this is what it says, so this is true in real analysis. So when you have this f prime is Riemann integrable and this capital F is differentiable, then you know that this theorem is true under the condition f of a is 0. But even if you put f of a is 0 in this setup, this will be not be true when the function f is any given function whose derivative is Lebesgue integrable. Is this clear or not? Maybe you can tell me. Is this fine with you? Take any function f which is such that, I mean which is of, let's say, okay, c1 you cannot take, so you have to choose some a function which is not uniformly continuous. Okay, and then not uniformly continuous and the derivative is integrable, f prime is integrable. Okay, so I mean you just look for a function which is not uniformly continuous and whose derivative is Lebesgue integrable. Okay, in that any function you choose, you will get that this equality will not hold. Okay, so actually this equality is contradicting from this proposition itself, and this is what I am trying to say, that suppose you have a integrable function. Okay, let me search for some blank page, let me tell you here. Okay, so let me mention it here. So suppose you have this f which is Lebesgue integrable on AB. Okay, this implies from this theorem what I have written, that this integral a comma x f dm1, if you consider this function, this is uniformly continuous and it is of bounded variation. Okay, this is true. Okay, so this is what proposition is saying. What I am saying, suppose, so my question is, let f is any function, okay, such that f of prime is Lebesgue integrable. Then consider this f prime of dm1 on this set Ax. Okay, then by the proposition, so Lebesgue integrable means that this will make sense, this makes sense. So let's say this is on AB, so this makes sense. Okay, now I am saying by above proposition, so my question is that is f equal to Ax f prime dm1? Okay, that is the question. Okay, the answer I am saying is that you choose f with above property, I mean, okay, or this could be answered. So by proposition, we know that this a comma x, this integral f prime dm1 is, let's say, uniformly continuous, right? This follows by the above proposition. Now the moment I say this is uniformly continuous, this implies that f is uniformly continuous, right? But you can choose f which is not uniformly continuous, but these properties hold. Okay, so if you can find a non-uniform continuous function such that the derivative is integrable, then you have the example, I mean, for which this will not hold. Okay, is this clear now?
Yes.
So you choose any function which is not uniformly continuous, but its derivative is integrable. Okay, and then you will get that this is not true. Okay. Okay, so now let's proceed further. Yeah. Okay. So now let's see some properties of this indefinite integral. So suppose this integral of f, okay, so f is any integrable function on AB, and this f integration over Ax is equal to 0 for all x in AB, then that would imply that f is 0 almost everywhere. Okay. The second property, okay, is this one, that suppose if you have a bounded measurable function, okay, and you define this one, f of x is equal to f of a plus this integral, okay, where f a is some constant, okay, as of now, because a priori, so what you have is this f, and this fa you are putting some value c, okay, that's it. So I should not write this fa. If you want, you can just put here, so this is nothing but some constant c. So this is the definition of capital F, that capital F of x is c plus this integral, okay, then where c is some arbitrary constant. Okay, then you say that this function f is differentiable almost everywhere, and the derivative of this capital F will be equal to the integrand, which is small f, almost everywhere. Okay, so this is in some sense, I mean, this is basically the first fundamental theorem of calculus, what it says. Okay, so this is true if the function what you choose, the small f, is a bounded measurable function. So if this f is bounded measurable function, then this integral of f is differentiable, right? So from here, so suppose this constant, you ignore this constant because you know the constant is always differentiable and the derivative is 0. So what this is saying, that if you have a bounded measurable function, then this function, okay, this indefinite integral is differentiable almost everywhere, okay, and the derivative of this is f of x. Okay, so this is what it says when this small f is bounded measurable function. Okay, so instead of this bounded measurable function, you just take this condition of integrability. So suppose this function f, small f, is integrable function, right? So in analysis course you see that instead of this you assume Riemann integration. So f is Riemann integrable and you define fx in this way, then you know that this fx is differentiable and the derivative is small fx. So it's basically the same. So the only difference is that over here in the hypothesis we had that it is bounded measurable. Now here I am assuming that it's just integrable function. So integrable means it is measurable, but we are no more assuming that the function is bounded. Okay. Okay, so this is it. Now let's go to the notion of absolute continuity of functions. Okay. So absolute continuous function is defined in the following way. Suppose you have a function. Okay, so I hope everything is clear so far. Do you have any question? Do you have any questions so far? Yeah. Okay, if there is no question, let's proceed further. So let us see what absolute continuous functions are. Any question? Okay. So suppose you have a function f which is defined from ab to r. Okay. It is said to be absolutely continuous if for any epsilon there exists a delta such that the following hold. So if you choose any collection, okay, any collection of disjoint intervals, and if you take the union, it is subset of AB. Okay, so this finite collection of disjoint intervals in AB, such that the length of this summation, okay, the length of this summation, the summation of this length is less than delta, then the summation of these length of function values will be less than epsilon. So if you have epsilon, so for epsilon there should exist some delta such that any disjoint intervals you take with the length, with the summation of length less than delta, then this length will also be very small. That's all. Okay, so this is how absolute continuous function are defined, and obviously this absolute continuous function implies uniform continuity of the function, because in particular you can choose. So suppose this f is defined on AB, so you just, instead of this collection, you just take one collection which is a comma b. Okay, now if this mod a minus b is less than delta, this would imply mod of, okay, I should not write ab but xy. Okay, so if this mod x minus y, then mod of fx minus fy will be less than epsilon. Okay, so this absolute continuity implies this uniform continuity of the function. Okay, now let's see a few example of this absolute continuous function. So any Lipschitz function you take, okay, and if you take any C1 function, then C1 function on bounded interval is nothing but Lipschitz function. So any Lipschitz functions are absolutely continuous, and if you have any integrable function, if you define some function in this way, again this is some constant, although this constant will be f of a, okay, but a priori when I am defining this function I should not write f of a. Okay, so suppose if this f is an integrable function and you define f of x in this way, or okay, so if you want to write this f a, you can write it in this way, f of x minus f of a. So this is my g of x. So writing f of a is also fine, I guess. Okay, so that's not a problem. I think here also you can write f of a. It's not a problem. Okay. So you are defining this function f, capital F of x, in this way. Then this capital F function is absolutely continuous. And in fact, the converse is also true. Okay, so that will be stated in the next, or in next slides, I guess. Yeah. Okay, see, so it's there in the next slide. So what are the examples? So any Lipschitz function you take, that is absolutely continuous function. And if you have any integrable function, you just take the integration indefinite integral, then this indefinite integral is also absolutely continuous. Okay. Okay. Now let's see some properties of this absolutely continuous function. If you have the function is absolutely continuous, then it is of bounded variation, and since it is of bounded variation, it is differentiable almost everywhere. Okay, so any absolutely continuous function is differentiable almost everywhere. Okay, and this is quite clear from here as well, right? So you saw in the last this one that if f is different integrable, then this function was differentiable. So okay, so I should not say in that way, because actually this converse is also true. Okay, so if f is absolutely continuous, then there will exist an integrable function small f so if f is absolutely continuous function, then there will exist a small f such that this holds. Okay, the moment I say this holds, that would mean that this f is differentiable by this theorem. Okay, but okay, if you are not going that way, so let's not go that way. But what you can prove, that if you have absolutely continuous function, that function is of bounded variation, and since it is of bounded variation, it is differentiable almost everywhere. Okay. Okay, now suppose if you have an absolutely continuous function whose derivative is 0 almost everywhere, then the function f is constant. Okay, in analysis we know that if f prime is 0, then f is constant. But if f prime is 0 almost everywhere, then f need not be constant, and this Cantor function is an example of that. So this Cantor function is differentiable almost everywhere, and the derivative is 0, as I mentioned initially in the when I started this session, that it is not it is differentiable almost everywhere, and the derivative is 0. Okay, but this Cantor function is not a constant function the way it is defined. Okay, so it is a non-constant function which is differentiable almost everywhere, and the derivative is 0. Okay, and because of this theorem it says that if this Cantor function cannot be absolutely continuous function, because if it was absolutely continuous function, then if the derivative is 0, then that should imply it is constant. But we know that it is non-constant function with 0 derivative. Okay, so the Cantor function is not absolutely continuous function. Okay, and this is what I was saying, that if you have a function f which is absolutely continuous, then fx can be written in this form, that there will exist an integrable function small f such that f of x is f of a plus integral of f small f. And in some books this is the definition they assume. Okay, so in some books this is how absolutely continuous function is defined, but you can find in some books that a function is said to be absolutely continuous if and only if there exists an integrable function f such that fx can be written in this form. Okay, so since this is if and only if, this can be adopted as a definition of absolutely continuous function. And in general, if you have been given some function and if you want to check whether that's absolutely continuous function or not, you would try to prove it in this way. Okay, so if you have such relation, then you say that the function is absolutely continuous. Okay, and one more thing what you can see here, that suppose f is absolutely continuous function, as I was saying above, that suppose f is absolutely continuous function, then you have this formulation that there will exist an integrable function such that this happens. But if you differentiate it, you will get f prime of x is f of x. Okay, so instead of this f, you can write f prime. So this is basically the first fundamental theorem of calculus, and this is true when the function f is absolutely continuous. Okay. Okay, so now let's move to few exercises. Okay, so suppose you have a function. Okay, so do you have any doubts so far? If you have, please let me know. I'll try to answer that. Okay, if there is no doubt, let's move to the exercises. Okay, so suppose you have been given a continuous function f, and the question is asking, will there exist a subset of 0, 1 such that, so suppose this f is given to on the 0, 1 f. So the question is, does there exist ab which is subset of 0, 1 such that if I restrict this my function f on this ab, then this becomes a bounded variation function. Okay, so this is the question. Okay, now suppose for now that suppose there exist. Okay, so we are just trying to find. Okay, so let me tell you that this is not true. Okay, so how you can see that? So suppose that this is true. Okay, so suppose there exist ab in 0, 1 such that g, which is restriction of f and ab, is of bounded variation. Then this would imply, since it is of bounded variation, this would imply that g, which is restriction of f on ab, is differentiable almost everywhere. Right? So it's differentiable on ab, and also so this, it should be differentiable, right? This is what it's saying. So if I want to tell you pictorially what it says, that suppose this is my 0, 1, it says that if f is continuous on 0, 1 and there exists ab and f is differentiable on ab. So do you know some example which is continuous and is nowhere differentiable? Have you heard of such functions? You must have, I mean, in analysis course, I guess. So do you know a function which is continuous but not differentiable? I mean, it's nowhere differentiable. So there exists, so this f, if you take Weierstrass, I think the spelling is wrong, Weierstrass. If you choose this function, this Weierstrass function is continuous and is nowhere differentiable. Okay, let me write what the function is. So this f of x is nothing but this is summation, okay, an cos of b raised to the power n, sorry, pi x, okay, where a is in this 0 1 and b is any positive odd integer. Odd integer such that this AB satisfies the following relation. Okay, so this function is continuous. So let me write the domain. So it's defined on the whole R. Okay, so this is continuous but nowhere differentiable. But what this theorem, I mean, if I assume that okay such thing happens, then what you are getting, that you are getting this function to be differentiable here but and continuous in the whole domain. But you can find this. So if you take this f as Weierstrass function, you know that it is continuous, but in any degenerate domain or any subset of 0 1, okay, whatever subset you choose, it cannot be a bounded variation. So the answer is no. Okay, because this is a contradiction. I mean, this is a contradiction, and the contradiction is coming due to this function, right? Is this solution clear? Answer me if it's fine or not.
Okay, sir.
Okay, it's fine then. Let's move to the next question. So, okay, so so this is what I was saying, that you have seen a theorem above that if, okay, yeah. So what I was saying, that if is of bounded variation if and only if f is a difference of two monotonic function. Okay, so here the question is that you have this f, you have to write f as a difference of two increasing function. Okay, so f as h minus g. So suppose you can write this in this way, that would mean that f is of bounded variation. Okay, so the proof that f is of bounded variation implies f is a difference of two monotonic function. We have to use that proof basically. Okay, so as I mentioned earlier, that you can write f of x as f of x plus this total variation of ax at f, I mean total variation of f in ax minus total variation of x in f. Okay, so you can write this in this fashion. So let's say this is your h, this is your g. So the only thing what you need to prove, that this h and g are increasing. So to show, so this is your claim. Claim is that h comma g are increasing function. Okay, so first I will prove that these are increasing function, and then I will find what this is. Okay, so I will have to find what this TAB, total variation of f, is, but initially let's prove that this h and g are increasing function. Okay, okay, so for the proof I'll use a lemma. Okay, so what this lemma is, so this lemma basically says that if you take, suppose this is your AB, then the total variation of function on AB, this interval, will be equal to the total variation on the two sub intervals which are disjoint. Okay, so suppose you have this, so what it means, so TAB of f, okay, is equal to, if you choose some point C, then TAC of f plus TCB of f. Okay, so this is what the lemma says. Okay, now for now let's assume this lemma. So change the color. So for now assume the lemma, then I'll prove that. Okay, so assuming this lemma, now you can clearly see if this is true. So I am showing that this is increasing function. Okay, so let x y, okay, let me write some other notation, wz maybe belong to AB such that this w is greater than z. Okay, and then you have to prove that ta comma w, so and then you have to show that ta comma w of f is greater than or equal to ta z of f. Okay, so from here what you can write, t of a w f is equal to t of abf minus write it in this way, t a w f is minus t a z f. Okay, so t a w this will be equal to t a, so z is lower, so this will be t w z, right, t z w of f, right? So it's like this. So this is your w, this is your z, and this is your a. So you are writing t a w, but taking the difference of t a w minus t a z. Okay, so you know that t a z is equal to t a w plus t w z. Now you are taking this this t a w here, so you are getting t a w minus, or you can take this here. Wait just a second. So t a w plus t w z. So okay, okay, so I have written it wrong. So here it's z and here it's w. So t a w is equal to t a z plus t z w. Now it's fine. So now if you subtract this t a z, then you will get t a w minus t a z is this one, and you know by the definition that this total variation is always a non-negative function. So this is greater than equal to 0. So this would imply t a w f is greater than equal to t a z f. Okay, so this proves that h is increasing. So this proves, was it h or g? Okay, so g is increasing. G is increasing. Okay, so this was about g. Now let's see about h. Okay, so what you can do, so f of x, if you see, again you can take w and z. So f of w and minus f of z, if you do, so this I can write, this is less than equal to the modulus of the value. Okay, this, and now if you, so suppose this z is less than w. Okay, now I am saying consider this difference. Now if you consider this domain z comma w, and if you take the partition as z comma w, okay, then this is nothing but the value of t at p and f. So where p is this one. Okay, so this is just by definition. Okay, this is there, and now this I can write less than equal to the total variation, because now you are taking many partitions and then you are doing so. So this is t w z of f, right? So by, I mean, just by definition, this also follows by definition. Okay, now this again, using this lemma, I can write this t w z in the following way. So here I wrote, right, so t w z Is it WZ or ZW? ZW. This is ZW. So TZW will be written as TAW minus TAZ, right? Now if I take, is this fine? No, something seems to be wrong. Okay, I should consider FZ minus FW. So if I do so, I'll get this. Yeah, now everything is fine. So if I take this on the left hand side, I'll get F of Z plus TAZ of F less than equal to F of W plus TAW of F, right? So this is nothing but H of Z less than equal to H of W, right? And you know that Z, okay, so I think I didn't write it, so let, here you can mention again similarly, let Z comma W belong to AB such that Z is less than equal to, yeah. So I am using it everywhere actually, this W everything, okay. Okay, so this proves that this H is increasing. Now the only thing we need to prove is the lemma. Okay, so now I will try to prove this lemma. Okay, first see, so how you can, so suppose this is your AB. Now if you consider any partition of this AB, so let P barabar A equal to x0 less than x1. Okay, I'll draw it again. So this is less than xn equal to B. Let's say that this is a partition, be a partition for AB. So this was the partition A, B, and then you are using x0, x1, x2 and so on. So this is your xn. Now this C, so okay, so I should write in the statement that this C belong to this open interval AB. Okay, so this C, let me write it here as well, C belong to AB. Yeah, so this C is lying somewhere here. So let's say this is some xk minus 1, this is, let's say, xk. Okay, so C is lying between some xk minus 1 to xk. Suppose that this is there, then so let P tilde, okay, be another partition which is x0. Let me write it here. P tilde, you consider x0, x1, xk minus 1, C less than xk. So you are basically, I mean, putting one more point in the partition P. Okay, then T of Fp, if you consider, that will be less than equal to T of Fp prime. Right? This is just, if you use the triangle inequality, you will get this one. Okay, so that's not a big deal, because if you say here in this, so in this TFP, you will get f of xk minus f of xk minus 1, right? Now if you use the triangle inequality, so you can get f of xk minus f of c plus f of c minus f of xk minus 1. Okay, so I mean, this is the reason why this inequality will hold. Okay, because the rest of the things will be same. Okay, so this is there. So this is there. Now if you see, if you want to take supremum, so if you want to take supremum over this P, okay, then that supremum is less than equal to supremum over such P prime. So I mean, this might be confusing, so let me speak it properly. So suppose this AB is there, this is your interval. Now this P is a partition of AB. You choose any partition of AB. Corresponding to this partition, there exists some partition P tilde in which you include one more point C. If C is there in P, then P tilde is basically P. Okay. Now if you take supremum over all such P, okay, then that P is what? P is any partition of AB. Okay, so that supremum will give the value to the total variation. Now P tilde is again any partition of AB, because this is coming from this one. Okay, so T AB of F is equal to supremum of over P T of FP is equal to supremum of P union C T of FP. Okay, what it means that if you want to calculate the total variation of F over AB without loss of generality, you can assume C is in the partition. Okay, so what it basically means, without loss of generality, because of this reason. Okay, without loss of generality, you can assume, one can assume C is in the partition P of AB. Okay, so if you consider some partition of AB, that will include C. Is this clear?
Yes, sir.
Okay, so you had that, okay, this partition is there of AB. Now what you do, so you start with a partition P, which is A equal to x0, x1, and then this is xk. Let's say xk is C, xk plus 1, xn. Okay, now you divide this in two partitions. So let's say this is P1. So P1 is A equal to x0, x1, xk equal to C, and then another partition is okay, let's use some other notation, y0. So this is yk, okay, y1, and then here it's C equal to z0 less than z1 less than z. So this is, okay, let's say zl equal to b. This was your b. So suppose what you do, you basically divide the partitions of AB in two partitions of this sort. Then T of P of this function, so T of F with the partition P is nothing but T of F partition with P1 plus T of F with partition P2. Right? You have just broken the partition in two parts, so this will be there. Now you just take the supremum over the partitions P. This will give you that T AB of F is equal to T AC of F plus T CB of F. Okay. Okay, so that's the proof. Okay. So do you have any doubt, or should I proceed? Okay, if everything is fine, now the goal is to find what is Tx of F. Okay, so now we'll try to find that. So you have been given F of x is sine of x. Okay, Now you have to find t a x of f. So what is this function? Okay, that's all you have to find. Okay, so start with here. So you all, so what you can do, if you recall this theorem, there is one t0 of not this one, so yeah, this one, so here this f of x is sine of x. Okay, that function is c1 function, right? F is c1. Then since this is there, this t a x of f will be equal to a x mod of f prime dm1, right? This is there for this function, so I'll use this one. Okay, so yeah, okay, so we know that t a x of f is equal to this, since f is c1. Okay, c1 0 to pi. Okay, okay, now since this is there, so what is the derivative of this sin x? This is cos x, so modulus of cos x over the intervals a. So over here a is nothing but 0, right? Okay, so I don't know whether, okay, so I'm here written a, so a here in is 0. Okay, okay, if you want, let's put it a only here, because I want to prove it generally. Okay, but in our case a is 0. Okay, so what is t0x? So this cos function, if you see the graph, cos function is like this. Okay, so in the interval 0 to pi by 2 it is positive. Okay, so let's say, so do it by case. So suppose x belong to 0 to pi by 2. Okay, if x belong to in this interval, then this modulus will be just cos x. So t0x of f is 0x cos of y. Okay, so let's write, so since we are in Lebesgue integral, we don't need to write x and y. So cos of y dy, because Lebesgue integral functions. Okay, so since this cos is Riemann integrable, so this Riemann integrable, and so Riemann integral and this Lebesgue integral are the same. Okay, since we are dealing with the bounded domain and the functions are also bounded. So now if you integrate this one, you will get sine of y, and if you put this you will get sine of x. So this is your t0x f. So this is your variation of this function f. Okay, so let's just call this, so did we call it something? So this was my g, so this is your gx. Okay, now suppose x belong to this pi by 2, so this interval is 3 pi by 2. So if x belong to this interval, then your g of x is equal to 0x. Oh, so first we'll, so let me write the definition. So this is 0x mod of cos y dy, and now you know in 0 to pi by 2 the function is positive, so it's cos y dy, plus pi by 2 to 3 pi by 2 this function is negative, so this is minus of cos y dy. Okay, now again if you integrate, you will get sine of y 0 to pi by 2 minus sine of y pi by 2 to 3 pi by, sorry, this will be x, right? this will be x. And now sine pi by 2 is 1, sine 0 is 0, so it will be 1 minus sine of x minus sine pi by 2 is 1, so this is 2 minus sine of x. Okay, now you choose x in 3 pi by 2 to 2 pi. Again, in a similar fashion, you can calculate g of x is nothing but 0 to pi by 2 cos y dy minus pi by 2 to 3 pi by 2 cos y dy, and then plus 3 by pi 2 2x cos y dy. Now again, if you integrate, this will be 1 minus sine 3 pi by 2 will be minus 1, and sine pi by 2 will be 1 plus this sine of x minus sine 3 pi by 2 will be minus 1. So we'll get 1, 2, 3 and then 4. So 4 plus sine of x. Okay, so the function gx can be given as, it was sine of x when x was in 0 to pi by 2, it was 2 minus sine x when x is in pi by 2 to 3 pi by 2, and this is 4 plus sine of x when x is in 3 pi by 2 to 2 pi. Okay, so f of x, so sine of x, which is your f of x, can be written as this sine of x plus this gx minus gx. Okay, so now this is increasing and this is increasing. Okay, so this is your hx. Okay, so this is how you can find the total variations of the sine function, and you can write sine as difference of two increasing function. Okay, now let's come to the third problem. So this is saying that suppose if you have a continuous function which is so continuous on 0 1 and it is absolutely continuous on epsilon 1, so except 0 it is absolutely continuous. Okay, then you have to show that f need not be absolutely continuous on the whole 0 1. Okay, that means you have to find an example which is continuous on 0 1 but not absolutely continuous on epsilon 1. Okay, so let's start with this a. Okay, so this example, if you recall, as I mentioned above, that this is x square and then sine of 1 by x square if x is not 0 and 0 if x is 0. What did I say about this function? That this function is continuous on 0 1, and I also showed you that this f is not absolutely continuous. Sorry, it is just a second. It is not absolutely continuous, right? Not of bounded variation. This is what I showed. This is f is not of bounded variation. Did you had something to say? Okay, so these are things that we have proved. I mean, I mentioned you, so this is quite easy and this I have proved initially. Okay, so since this is not a bounded variation, okay, it cannot be absolutely continuous. So from here you can say f is not absolutely continuous on 0 1, because I mean in one of the theorem I said that absolutely continuous function implies that the function or of yeah, so I proved in the above that absolutely continuous functions are of bounded variation. Okay, so since this is not a bounded variation, it is not absolutely continuous on this 0, but I have to prove this one also, right? So it should be absolutely continuous on epsilon 1, then I am done. Okay, so you know this function f of x, so this f is in fact c1 in epsilon 1. So if you go away from 0, this function is quite nice, it is differentiable and the derivative is also continuous. So this function f is c1, and this implies that f is Lipschitz, and this implies f is absolutely continuous. Lipschitz on 0 epsilon 1 on epsilon 1. Okay, so that's all. So you have this example which is continuous on 0 1. It is not absolutely continuous on 0 1, but it is absolutely continuous away from 0. Okay, so we have given one example. Now let's go to the B part. Okay, in B part what it says, that suppose your function f is continuous on the whole domain 0 1, it is absolutely continuous away from 0, and if the function is increasing, then it is absolutely continuous on 0 1. Okay, so continuity on the whole domain, absolute continuity away from 0, and if the function is increasing, that would give that the function is absolutely continuous on the 0 1. Okay, so so let's start with this proving absolute continuity over 0 1. So first let us see what is given to us. Okay, so this function f is continuous on the whole closed interval 0 1. So in particular it is continuous on 0. So f is continuous at 0 at x equal to 0. So what does this mean? This means, so okay, so since we want to prove absolute continuity of this on 0 1, let us start with some epsilon. So let epsilon greater than 0 be given. Okay, now since f is continuous at 0, so there exists delta 1 greater than 0 such that mod of fx minus f of 0 is less than epsilon by 2 if mod of x is less than delta 1. Right? So this is just the definition of continuity. Now you have been given that f is absolutely continuous on epsilon comma 1 for any, okay, so I mean yeah, okay, so I'll just write. Okay, so you have been given that f is absolutely continuous on any epsilon 1, right? So in particular you can say it is continuous on, absolutely continuous on delta 1 comma 1, right? So I can write delta 1 comma 1. So f is absolutely continuous on delta 1 comma 1. Now what does that mean? This means that there exists some delta 2 such that for any finite disjoint, so for any disjoint collection x I comma y I is from 1 to n, okay, in this delta 1 comma 1, okay, such that summation mod yi minus xi I from 1 to n is less than delta 2, will imply that summation I equal to 1 to n mod of fyi minus f of xi is less than epsilon by 2. Okay, so this is just I have used the definition of absolute continuity on the interval delta 1 comma 1. Okay, so this is all what we had. Now you choose delta, you define delta to be minimum of these two, so delta 1 comma delta 2. Okay, if you want, let's name this as 1 and this as 2. So now you define delta as the minimum of delta 1 and delta 2, so that 1 and 2 both holds true. Okay, so since we want to prove absolute continuity of this function f on the whole interval 0 1, we'll have to start with some partitions of this whole interval 0 1. Okay, so let this xi comma yi, so I from 1 to let's say some other m, be a collection of this joint subsets in 0 1, disjoint intervals in 0 comma 1, such that this mod yi minus xi I equal to 1 to n, this is less than delta. Okay, so this is the delta what we have chosen. So I am saying that for this delta my absolute continuity argument will be true. Okay, now okay, so one thing what you can do, that when I am considering this interval, this collection, okay, so you can consider that xi, so without loss of generality you can consider x1 less than y1. This is anyway true. Now this y1 is less than x2. Okay, so I am considering my this collection to be in this fashion. Okay, so this is xn less than yn. Okay, so this is the way how this collection is considered. Okay, so this you can always do just by renaming the things. Okay, so it's not a very okay, so this is how I am assuming this collection to be. Now you can look what you can do. You can basically partition this again, so that one of these will lie in 0 delta 1 and the other will be in delta 1 comma 1, because in 0 delta 1 I want to apply these two results I want to apply. So I'll have to split this partitions or this collection in two halves, one which is contained in 0 delta 1, the other one will be in delta 1 comma 1. Okay, so now let this xi yi, so I from 1 to let's say m1, okay, be contained in 0 comma delta 1. Okay, and this xi comma yi I from 1 to m1 to m be contained in delta 1 comma 1. So here so now here you can clearly see this delta 1 comma 1 I considered that it is absolutely continuous in this region, and here I will use the continuity of function at 0. Okay, so here like there could be a case when this delta 1 is one of the yi's or xi's. Okay, so if this delta I belong to some this xk comma yk, then you can split that interval in two parts. Okay, then consider this xk comma delta and delta comma yk. So now this will go in this collection and this one will be in this collection. Okay, so this will go here and this will go here, because I want this collection to be contained in this interval. Okay, so that's why. Okay, so now all the setup is done. Now just you consider this summation. Take I equal to 1 to m mod of f yi minus f of xi. Okay, so now you just split in two parts, where I is from 1 to, okay, so the main thing is here is, okay, so what you can do is m1, so let me write it, fyi minus f of xi. So I'll have to use that increasing thing, right? So this m1 to m mod of fyi minus f of xi. Now you know that this function f is increasing, so that's why you can remove the modulus. So I equal to m1, and then over here what you can say, f of yi minus f of xi. Okay, and then again, okay, so so here is just, here we do just, you want to use this absolutely continuity thing, so here we don't need to split it. We don't need to use that f is increasing, so let's keep it as it is. Okay, now let us try to see what this gives. Okay, because here I don't want to deal with this summation, I just want to deal with the fact that f is continuous at 0. Okay, that's all I want to use. So let us first see what this is giving us. Okay, so this summation m1, I can write this as, so this is, so if I expand this, what will this be? So this is f y1 minus f of x1 plus f of y2 minus f of x2 plus f of y m1 minus f of x m1. Okay, now if I take this f of y1 separately with this minus f of xm, okay, or just a second, I want to write this as, I will have to ignore this summation, or no, I think you better, okay, don't do in this way. So what you can do is, fy1 fy2 yeah, okay, so see, this function is increasing, right? So if you remember, this x1 is less than y1, this x2 less than y2. Yeah, so this fy1 minus fx1 is positive so far. So what I'll do, I just take fx1 outside and this fym1 outside. So if I take fym1 minus fx1, okay, now if I club this, so this and these are gone. Okay, now if I club this fy1, this f of x2, okay, now you know that f of x2 is larger because it's increasing, so this quantity will be negative. Okay, so what I can write, f of y1 minus f of x2, right? In the same way, this f of y2 will be paired with f of x3, so you can write f of x3, sorry, y2 minus f of x3. Okay, in the same way, at last what I'll get, f of x m1 minus 1, sorry, y m1 minus 1, just let me keep it here. Yeah, so at last I'll get f of m1 minus 1 minus f of x m1, right? Just the following the pattern. Okay, now you know that all these quantities are negative. just because f is increasing. Okay, so you can write this one less than equal to f of y m1 minus f of x1. Now what is x1? So okay, so x1 need not be, so let me write x1, and this is 0, right? I mean these whole things is, this whole quantity is less than equal to 0. Okay, so this I can make it 0. Now you know that x1 is greater than 0, right? Because you chose this partition is contained in 0 delta 1. So this x1 will be greater than 0. So this f of 0 will be greater than f of x1. Okay, so minus of f0 is greater than minus of fx1. So I can replace this minus of fx1 by f of 0, right? This is what I can do. Okay, now this function is increasing, so this is nothing but the modulus, or if even if this function is not increasing, I can write, so here it will be f of y m1 minus f of 0. Okay, if okay, so this is how you can write this function, this quantity in modulus. And now since this mod ym1, if you see, how did I partition this thing? I partition this was contained in 0 comma delta 1, right? And this y1 is lying somewhere here, so this ym1, so from y1 to ym1 all are here, right? So ym1, this modulus of this one is less than delta 1, right? So this quantity is less than epsilon by 2, since mod of ym1 is less than delta 1, right? So this is just by using the continuity at 0. Okay, now so this was, so what you did, you can make this quantity, so let me call this star, so you can make this quantity less than epsilon by 2. Now the only thing remain is to make this small, and this is already small, right, just by absolute continuity. So to make this less than epsilon, you need that I equal to m1 plus 1 to this m mod yi minus m xi. Okay, so this quantity is less than equal to the whole summation I equal to 1 to m yi minus xi, and initially you assume that summation yi minus xi is less than delta. So this is less than delta, and delta was minimum of delta 1 delta 2, so this is less than delta, so what was required for absolutely continuous, so delta 2, so this is less than delta 2, right? So this partition has some length less than delta 2, and so this will be less than epsilon by 2. Okay, so this is the reason for this one. Okay, and for this being epsilon by 2, this is the reason. Okay, so overall, so what you obtain is summation, so this quantity so you proved that this quantity is less than epsilon. Okay, and this implies that f is absolutely continuous on 0 1. Okay, so this was about the second part. Now let's see what third part says. So here you have been given this fx, which is root x, and you have to prove that this is absolutely continuous. Okay, so, and this is not Lipschitz, that I hope you know how this is not Lipschitz, but okay, anyway I will write that. So suppose this is the function f of x is given to be root x, okay, and x belong to 0 1. Okay, so you know that this function f is continuous on 0 1. Okay, you also know that f is c1, so let me write it here. You also know that f is c1 on epsilon comma 1 for any epsilon, right? Because if you take the derivative is 1 by 2 root x, and at x equal to 0 it is not bounded. So that is why this is c1 on this. So 1 by 2 root x is not continuous basically at x equal to 0. So f is c1 on epsilon comma 1 for any epsilon greater than 0. Okay, and also these two things, this with this imply that f, so this, since it is c1, it would imply that f is absolutely continuous on epsilon comma 1. Okay, and since it is absolutely continuous on epsilon 1, it is continuous on 0 1, so f is absolutely continuous on 0 1 by the b part. Okay, by b. Okay, and so this was about proving that f is absolutely continuous on 0 1. Now you suppose, so you want to prove that f is not Lipschitz. Okay, so suppose if possible f is Lipschitz. When you say it's Lipschitz, it means that mod of fx minus fy less than L mod x minus y for all xy in 0 1. On 0 1 imply there exists L greater than equal to 0 such that mod of this thing happen. Now from here you can write mod of fx minus fy upon mod x minus y less than equal to L if x is not equal to y. Okay, now if you take the limit, so take limit y going to x or y going to 0 plus or y going to 1 minus. Okay, so if x is the boundary point, okay, so this is how you take the limit. So you will get f prime at x less than equal to L. Okay, so this means that the function, the derivative of the function is bounded, but f prime x equal to 1 by 2 root x is unbounded on 0 1. Okay, so this is a contradiction. So this function f is not Lipschitz. Okay, so this is an example of absolutely continuous function which is not Lipschitz. Okay, but any Lipschitz function is absolutely continuous, right? Yeah, so any absolutely continuous function is Lipschitz. I think I have written it somewhere. Any Lipschitz function is absolutely continuous. Yeah, so any Lipschitz function is absolutely continuous. Okay, and this is also quite easy to prove. It's not a big deal. So you just have to use the Lipschitzness, get that. Okay, so one more question. So this one, so I'll just sketch the proof of this one. So you have been given that f is Lipschitz on R. So this implies f Lipschitz means there exists L greater than equal to 0 such that mod of fx minus mod of fx minus fy less than equal to L mod x minus y. Okay, now you have to prove, and G is given to be absolutely continuous on AB. So you have to prove f compose G is absolutely continuous. So let xi, let 0 x a equal to x0 x1, sorry, why I am writing this. So let xi comma yi 1 to n be a disjoint collection of disjoint intervals, be collection of disjoint intervals in AB. Okay, now so try to figure it out what this f compose G yi minus f compose G xi is. Okay, so for proving absolute continuity we need to say that this quantity should be small if the summation of the length of each of the interval is small. Okay, so let's try to figure out what comes. So this quantity less than equal to I equal to 1 to n, this is equal to f of g of yi minus f of g of xi. You know that the function f is Lipschitz continuous, so you'll get L summation I equal to 1 to n mod of g yi minus g of xi. Now okay, so now you have to use the absolute continuity of g. So you know g is absolutely continuous, so you can make this quantity less than epsilon by L. Okay, so you choose initially only you choose epsilon to be greater than 0. Let epsilon greater than 0 be given. Okay, so you can make this quantity less than epsilon by L if summation mod yi minus xi I equal to 1 to n is less than delta. So this is by absolute continuity of g. Okay, and this is equal to epsilon. So you prove that this composition is an absolute continuous function. So this implies if compose g is absolutely continuous. Okay, so you have to you have to be careful about the ordering. So the function f which is coming first here is Lipschitz. Okay, and the other one is absolutely continuous. Okay, so that's all for today. Do you have any question? Yeah. Okay, if there is no question, then I'll just stop the session here.